Okay, welcome everyone joining us on YouTube, on Zoom, or also here in the classroom as part of a guest lecture from Dr. Jessica Granderson on maximizing smart building infrastructure to scale grid interactive buildings. Dr. Jessica Granderson is a senior scientist and interim director of the Building Technology and Urban Systems Division at the Lawrence Berkeley National Lab. She's a member of the Whole Building Systems Department. She holds a PhD in mechanical engineering from UC Berkeley and an AB in mechanical engineering from Harvard. Her research focuses on energy management and information systems, fault diagnostics and control, and advanced measurement and verification. She is the recipient of the 2015 Clean Energy Education and Empowerment Award for Leadership in Research and the 2020 Federal Laboratory Consortium Award for Excellence in Technology Transfer, and was a 2020 Women at the Lab honoree. From 2021 to 2022, Dr. Granderson served as a director for building technology at the White House Council on Environmental Quality. Without further ado, please take it away. Thank you for having us, for being here.
Well, thank you so much for having me. I've been looking forward to this. It's a really nice way to kick off the day here. I have spent my career working at the intersection of energy technologies, the people who use them, and the organizational processes that they are embedded into. In my role here at Berkeley Lab, I lead our program in smart building software technologies, particularly for commercial buildings. And as mentioned, I'm the interim director for the division. Our portfolio is broad. It spans commercial, residential, high-tech, industrial facilities, the full gamut of buildings and industry. The work covers anywhere from like earlier stage development into very late stage R&D, market facing, demonstration, field validation, and deployment. And the work I'm going to share with you today kind of spans the middle and the edges of that. And I think you'll see the ways that that is true. So we're going to be talking about grid interactive efficient buildings, maximizing the infrastructure to scale these strategies within our commercial building stock. And I'd like to just begin with some overarching context. As we have, as an industry, as researchers become more fluent in the how-to of decarbonization, we have really got new findings at our fingertips that shows us that efficiency and demand side flexibility are critical to making our energy transition both reliable as well as affordable. We have, of course, very aggressive national goals for economy-wide emission reductions. We're trying to hit 50% by 2030 and net zero by 2050. Berkeley Lab work has shown what that looks like for the building sector. What you see here are different colors for different scenarios, an x-axis that goes from present to 2050, and a y-axis that represents total stock-wide building emissions. What the results show us is that you can kind of see in the pink line what a high rate of electrification only does for us. It's really that most aggressive case of, yes, electrification, also deep efficiency, and a clean grid that's going to get us onto that blue trajectory. And that's what we need to get to a level where we can plausibly offset our remaining emissions for that net zero target. I'll give a couple examples of how this speaks to critical demand side flexibility. This is a case of California, showing how electrified buildings and vehicles will increase our loads on the grid and also change the timing of that peak. You see summer on the left, winter on the right, and shoulder seasons in the middle. Currently, California, a summer peak of about 30 gigawatts. Now, the blue lines show cooling, the red heating, and the pink EVs. If you focus on that heavy dashed black line, that's the net load on the system after we take out distributed PV, utility scale wind and solar. By 2050, with aggressive electrification, we see that peak increasing over 30% by 10 gigawatts to a winter peak. We're also shifting the season of 40 gigawatts. Now that shift from summer to winter happens to be when there is less renewable generation. The second dynamic we're seeing, this is again a California example, is that as we increase the renewables on our grid, we're seeing a mismatch between supply and demand. So you can see here a literal order of magnitude increase in curtailment of our renewables over the time frame depicted in this plot. We hit last spring an all-time high of 700,000 megawatt hours curtailed. And we're only accelerating towards 100% clean electricity goal by 2045. So these mismatches are expensive. They also present real challenges to reliability, as we've seen, like not just in California, but nationwide. This all speaks to the need to really focus on our buildings and our vehicles to provide critical grid services in support of that energy transition. So that means efficiency overall to reduce the loads, storage so that we can shift energy use to times of day when those electrons are cleanest, when they're least expensive, and when they're most abundant. And then control, further reducing the peak, lowering our investments in generation and transmission capacity. Now, recent work from Berkeley Lab has shown that building measures alone could save over $100 billion in avoided costs in bulk power system investments by 2050. The avoided costs themselves could cover 80% of those demand side measures. They are mostly HVAC, envelope, and water heating measures. The plot on the right shows really the role of efficiency and demand flexibility. It's only the lightest bars that are electrification. This is before we even get to the distribution grid level. That's, of course, where if we're successful in electrifying at the rates that we want, we're going to see a lot of infrastructure constraints and further investments in maintaining the grid. So this value can be captured through the integrated use of distributed energy resources. Those are not only or exclusively about value to the grid. This is resilience benefits and bottom line benefits to owners. So we are really talking about exercising thermal mass of buildings, exercising thermal storage, as well as mobile and stationary electric storage, combining that with standard communications protocols, pursuing policies that require us to use those standards, and layering in then the responsive control. Now we're talking today about how we're leveraging infrastructure for scale. And I went to show work from Berkeley Lab's CalFlex Hub that showed typical architectures to convey grid signals to building loads. And there's many pathways shown here. These are very much a result of existing technology capabilities crossed with the grid services and the marketplace of providers to acquire those assets from buildings and provide them back to the grid. And there's a lot of different ways these signals can reach our controllable loads. When we think about like medium and large size commercial buildings, the most common today are OEM cloud to device. That might be like a responsive water heater or thermostat. That's that path shown at the very top of the image. I'm going to talk a lot about how we combine a building automation system. In this architecture diagram, that's defined as a building central entity. How we use that along with smart building analytics tools, energy management, and information systems, which in this architectural schematic are shown or represented by the third-party cloud element of the schematic. Before we get to lots of thermal storage or distributed energy resources, we can look to our common and proven HVAC strategies for demand flexibility. I think this is really important to kind of start from ground level of what we know we can reliably do in our buildings. So I will talk about zone temperature set point adjustments and pre-cooling to shift loads to deepen or extend a load shed. We have used in the field for years chilled water temperature resets, limiting like fan speed or coil valves, and doing controlled charging of chilled water or hot water storage. I do want to recognize that the demand flexibility that we're looking to provide from our buildings is tied in different ways to grid services. So this is kind of like the buildings perspective and the grid perspective. And DOE did some foundational work several years ago to really bring this together in a consistent framework and provide clarity around those different perspectives. So from the demand side, we're like efficiency, shed load, shift load. That translates into various different types of services that are of value to the grid. And it's useful to have in mind, which of these we're targeting through the work that we do when we implement within buildings. Those services and management strategies can further be characterized by like how long do they last, how quickly do you need to respond, how commonly are you looking to provide the service. We are long-term moving to a place of more continuous demand flexibility, and we can hold that out as kind of where we're going. And then there's additional context for where we're at with existing markets and programs. Programs that incentivize load shed available nationwide, many service territories. We're seeing time of use rates as a mechanism to encourage shifting load to different times of day. We also recognize, particularly in the large commercial context, that there's strategies around demand limiting that can be very useful in avoiding peak demand charges, which can be a huge component of the bill. Now, technically, those are not a service back to the grid, but they're an important way that we see the uptake and adoption of different flexibility strategies. Now, I want to move into how we're really thinking about smart building software as already being able to unlock scaled efficiency and demand flexibility, right? The data shows, the studies show that we need those hand in hand to reach our goals. My team works extensively in what we refer to as energy management and information systems. So these are the software tools that are pulling in data from many sources, centralizing them, and then serving up either advanced analytics or like fault detection and diagnostics. So I show those in the screen grabs on the bottom right of the slide. That's constantly analyzing operational data from HVAC systems, identifying problems with equipment, stuck valves, stuck dampers, problems with control, simultaneous heating and cooling, scheduling, and so on. There are also technologies that emphasize predictive HVAC system optimization. And those capabilities have been separated into different products. My team conducted the largest study of the costs and benefits of these technologies that we are able to get from the literature yet. 500 million square feet of install base, over 6,000 buildings in the data set. And we found that users of FDD are saving on average 9%, and they're doing it with a 2-year payback. The predictive optimization technologies are less prevalent thus far in the marketplace, so we had a much smaller sample size in this study of their costs and benefits. Oopsie. What we know from all of this work is that the FDD technologies are saving impressively. 9% 2-year payback, that's pretty good. Pretty good for our work in building efficiency. Here's the issue, the bottleneck: getting the faults fixed, getting the base controls working right is still an extensive multi-step process. We're not quite getting to the full potential because, like, our building's workforce is really bogged down in, like, finding a problem, submitting a work order, often getting yet another party to come and reprogram the control system. And it's not until many, many months later that a lot of these problems are getting resolved. The work that we're doing now is looking to change the paradigm here, to bring fault diagnostics together with control optimization in product offerings, same offering, for the first time. Now, historically, as I mentioned, these have been very different types of products that are out there. What we've done is added a two-way write capability to the fault diagnostics. And then I'm going to skip down to number 3 on the right-hand side. Then we've folded in complementary logic. So we complement the FDD with the logic to correct problems and implement best practice control. Now, number 2 is how we do the reverse. We can work with the predictive optimization control providers to bring critical FDD logic into their offerings. I'm going to talk mostly about that step 3. So effectively what this does, it short circuits that business as usual process. We can, through this integration and the two-way interface with the control system, we can automatically push corrections and improvements out to our buildings, new sequences, fix control faults in a matter of hours as opposed to months. This could be done by operational staff. This could be done by managed service providers. So correct faults, we can optimize control. We can also bring in automated demand flexibility. And I'll take you further down the road of how we've done that. But what I want to really emphasize here is, like, why is this so critical to scaling? So the EMIS, the analytics technologies, have already done the very hard work in their core offerings of integrating across all kinds of different automation systems, protocols, HVAC configurations. Like, they've done that. We're now able to bring in the ability to then utilize that modern software environment. This is usually like cloud-based software as a service, for much more nuanced optimization and demand flexibility, as well as that kind of push update paradigm. The BAS infrastructure is here today. This work looks to really utilize it to its full potential and maximum value. Because what I show on the right, if you're doing something like demand flexibility through just natively working within the BAS, I show the screen grab, you're kind of working in these very different environments. So limited programming, time consuming and expensive, and requires kind of a good bit of either operator or the third-party contractor caretaking. We've been working with a growing set of product providers for smart building software tools to bring these enhanced correction and demand flexibility capabilities into their product offerings. And I think it's a lot of times as researchers, we work in kind of rolling our own. And it's really hard to then bridge that gulf into getting things into commercial product and platforms that are actually in our buildings. So we were very intentional to figure out a partnership mode where we could work with across any provider that was interested in following this direction. And so here's the model. Like the lab, we develop open on paper specifications. We transfer those specifications to our partners who can instantiate them in their like development product environments. They can then refine from the spec as needed. They can add to it and retain their IP. What we ask is that our partners bring back data from testing these strategies in the field so that we can document the efficacy. Now, in the case of one product out there, which is SkyFoundry's SkySpark, that is not like fully packaged, populated with analytics software as a service. It's more a platform that is programmed by service providers in the industry. This tool is used by operations at Berkeley Lab, where we did a lot of this work in our backyard. So in that case, we were able to also share reference code, but it doesn't necessarily make sense to try to do that with our other commercial partners who have software as a service offerings. Our process over many years was to work with a set of inaugural partners, have a set of industry advisors who we hoped might be second wave adopters or partners in this work. When we were able to bring back some field results along with our open specs, we're then positioned to engage additional partners. And that's really the mode that we're in today. I acknowledge every one of our fantastic partners here. This is very hard work. Several more in progress who we're ramping up with. Now, at the end of the day, our team works extensively with building owners and operators who use these analytics technologies. And as we're able to build up an ecosystem of providers who offer this through product and service, we can turn to the owner audience and continue to provide them with technical assistance to pilot these new capabilities, to specify them, to ultimately procure them. So that's kind of the arc of like from lab to how we work with multiple partners at the same time, allow IP to flourish while still having open specification and open results from the field that will provide the proof points and evidence that we're successful in these strategies. Here's an example of just one example that I want to go a little deeper on, which is load shedding and doing it with a zone temperature adjustment. Remember, I talked about a lot of different ways that we typically do demand flexibility with our HVAC systems. So without smart building software, the way we would do this with the BAS, we might find a global point that we could adjust all at once. We might go like one by one. We might not even do zone temperature adjustment. We might go straight to limiting strategies. And the operator can be a participant in making temperature adjustments more aggressive through the duration of a flexibility event if they would like. In the more full-featured software-based approach, we can leverage those more extensive programming capabilities, and we can follow a more nuanced zone-by-zone approach to these adjustments. And let's talk about that. There's a lot of ways you can do this, and our spec has articulated like 4 or 2 of them, depending on how you want to count. One is that you might define a maximum zone temperature set point. Like never will I go above 78 degrees. It's too brutal for my occupants. You could do that all in one step, blam. You might do that, or you could do it with a ratchet-based approach where you go a little bit at a time. Maybe you don't even go all the way to the max if you're happy with the response that you're getting. That may be an operational policy perspective. That might also be just contingent on the equipment that you're interfacing with. You don't get a lot of modulation on the package systems in the way that you do from the built-up VAV systems. The other flavors are which is really where we need to go. If you think about long-term, anytime, continuous demand flexibility, like targets, having our control in a more closed loop manner where we have a target that's either, you know, I want to hit a certain load or a % reduction, and we can control the systems accordingly. Within our spec, you know, so we articulate those different flavors. There's other details. So we've incorporated things like, and this is the beauty of kind of having the programmable software environment. We can pre-qualify zones for adjustment. We can re-qualify them through the duration of an event. Partners define the specifics of exactly how they want to do this for their customers. They can define a wait time before a ratchet, a step size of a ratchet, and precisely how it is they want to return zones to their original or standard set points to avoid rebound, which would like set a new peak, which wouldn't be helpful at all. So broad brushstrokes that we define and then partners implement and instantiate in the way that makes most sense to them. They refine and can add into the mix their own IP for how this is being delivered within their products. When I say open spec, I wanted to give an example of what we really mean by that. So we have logical flow diagrams. So on the left, I kind of show the whole chain for zone temperature-based adjustment to do a demand shed. We have English language description. So I pulled out a little excerpt there for the zone qualification check. A little bit of like pseudocode snippets to go along with it to further convey what we mean by the diagram, what we mean by the English language. And then I show on the bottom right, this is just a blow up of that zone qualification step of the full process, which concludes with that rebound management. Gosh, my mouse is very jumpy. We do have other strategies in our specification for demand flexibility, pre-cooling with a temperature adjustment, chilled water temperature, set point resets. And, you know, this is ongoing work. I expect us to articulate some of those other best practice methods on fan speed and coil valve limiting, maybe incorporating storage. We'll see really how things progress. I want to share some actual results from the field. This is demand shed with pre-cooling from zone temperature adjustment. We did this using our SkySpark instance in the operations office associated with our Flex Lab experimental facility here at the laboratory. So this was, this ops office is like a small portable with served by a couple units. So very straightforward for us to drop into to kick the tires before handing over to partners for implementation. So 2 units, the infrastructure that was connected with, we went from the FDD to the smart thermostat, and we manipulated set points there through the right back feature. We had real-time feedback and an established load target, and we could sequentially shed across the units and do a set point ratchet to preserve that load shed throughout the duration of several hours. Otherwise, if you make one adjustment, you know, you might shed for a while and then float back up as you need to satisfy the cooling needs of the space. We did a gradual return to avoid the rebound. So the data is shown on the right. So the dashed lines are the set points for those units. In the beginning, they're low at that 1330 for the pre-cool. Then they ratchet upward through the duration of the shed. The solid red and blue lines are the actual temperatures for the zones. And then the black is the total load. So you can see that around just after that 1330 time period, we're gonna drop load on one unit, and then the next unit that will persist as we ratchet the temperature set points up. And then we return to our basically our pre-event load levels, and we do that without a huge spike at the end of the period. This is an example, a second example, working with a partner who put this into a different product environment and tested it at a retail site in Virginia. So this was 18 rooftop units interfacing with Niagara building management system, again, using the zone temperature set points. In this case, each of those 18 units were prioritized based on zone temperature at the start of the event. The calculations here for demand are based on virtual meter calculations that include the known capacities of the units. Again, there was a stagger back to avoid rebound. And so this is shown, the baseline is shown in orange. That's what the HVAC consumption of these 18 units would have been in the absence of any demand flexibility. The blue shows you the shed starting at about 1500 hours. The green is the shed command signal across this set of 18 units. So you can see that more and more units are brought in as more and more load is shed, and the around 2100 this test concluded. Since I have the time, I want to give a couple of other examples, and this is now kind of zooming out to all of the things that we can do when we have two-way capability and enhanced logic with our fault diagnostic systems. And I'm going to show a couple other examples as implemented by Berkeley Labs operational team who run all of the facilities here at our laboratory site. This is zone temperature set point correction according to operational policies. So operators may change zone temperature set points for all kinds of reasons. For a central energy management or facilities team, this can be monitored and corrected back to the actual operational policy intent. Here I'm showing a screen grab. The red shows cases where the heating and cooling occupied and unoccupied set points are different from what the management team has defined as standard. Green means we're good, like an unoccupied cooling set point of 80, that was fine. What those reference operational intent can be compared to the actual. And then I'll show kind of, if you can see my mouse, so it's a little gray here, but you can push reference temperatures now back out to those zones that have diverged from policy. And the screen grab on the bottom shows what happened when the operator did do that, or the facilities team did push that reference temperature back. The trends show that that right action was indeed executed and then released again at the conclusion of the test. So other things you can do for continuous efficiency when you have access to write back temperature set points from a portfolio-wide kind of central standpoint. We talked about demand flexible control. We've also implemented best practice all around, continuous supervisory from the analytics. And in this case, this is AHU level supplier temperature and pressure reset strategies. And we've implemented, this is also all in our specs, guideline 36, standard trim and respond. And the team really wanted to pursue this here so that they could kind of minimally modify existing BAS logic. So that notion of just having more of a push-based paradigm. So on the top plot, the cooling set point is shown in light blue, the supplier temperature in that darker blue. And you can see that on the bottom, these are the incoming cooling requests. And as the cooling requests mount and grow across the day, then you see the system respond, the cooling set point drops, the supplier temperature responds accordingly. So this is the strategy in action being delivered through the analytics interfacing with, and we did this for different makes and models of control platforms as well. A really nice piece of this, since we've got the analytics in place, well, let's identify rogue zones and let's disqualify their calls for cooling. And that's this strategy in action. You could define that different ways. In this case, it was the faults that would disqualify a zone, leaky reheat valve, not meeting the airflow set point, or a cooling set point that was just too low and overly aggressive anyways. You can see in these plots that on the bottom, you're kind of seeing the dark shading. It's only until that like 4 or 6, like late afternoon period where we're actually getting to a place where the requests are legitimate. And so we have an impact shown on the top screen of that set point coming down and then going back up. This amounts to, like, if you think about this day after day after day, unit after unit after unit, this is significant savings from being able to address the challenges with zones that we know have other issues and shouldn't be pushing the whole system to max. Oopsie. I show in the URL website that documents this work in full, from the fault correction into the supervisory controls, demand flexibility. We're also taking on automated functional testing through some of this work. The website shows what is a living and growing set of documentation. So there are success stories from some of the earlier, or I would say farther along work with some of our partners, publications on our field test results. We have anticipating that we want to kind of prime technology users to know what's coming. We have implementation guidance for owners. And in that unique case of the SkySpark users, some reference code from where we've implemented in that environment in our own backyard. So I'd encourage folks to take a look here and see what's posted. This very rich and ongoing work. We definitely, the demand flexibility stuff is just ramping up. It's kind of the newest in the fold that's starting to get out there. So I'm very excited for that. More field testing, more transfer to our growing partner cohort. We're going to, as I mentioned, expand that open spec for additional best practice vetted demand flexibility strategies. Berkeley Lab and our collaborators across the industry, research, and other labs have been pursuing semantic enrichment of data. So working in the realm of the coming ASHRAE standard 223, haystack, brick, those kinds of models. So we will be and are in the process of codifying these demand flexibility strategies in a Python library that has the associated semantic features. So starting to connect the dots to show how we can facilitate application portability and auto configuration as this semantically enriched data becomes more and more prevalent across our buildings. And then, as I mentioned, our work in this team is definitely with product and service providers, but also back with the owners and users of the technology. And we certainly look to, as our base set of evidence from the field grows, and as that ecosystem of where you can actually get this in the market also matures, then we'll be able to turn to that owner audience and support them in piloting and procuring these emerging capabilities. I'm going to kind of wind up with some concluding comments around how, like, big picture, how this work fits and how we see it as really central to the future of our buildings and our smart buildings as we pursue those extremely aggressive goals for the energy transition. We are at a place of historic investments in retrofits and electrification for our building, right? We have the Inflation Reduction Act, we have the bipartisan infrastructure law, that is flowing. And what we know from our decades and decades of work in building operations, commissioning, and so on, is that these technologies are critical for ensuring persistent performance and enduring value of those capital investments. We have a retiring workforce in the commercial building sector, and the next generation expects, just as in every other aspect of our lives, networked and intelligent systems. So this technology family and evolving set of capabilities is bringing that automation and modern tool set to the building O&M practices and industry. We've got this incredible mobilization around climate urgency and around speed, scale. At the same time, this is happening as we ask more and more of our buildings. We have to provide a healthy indoor environment. We want them to be connected and flexible to coordinate with the renewable grid. We've got to integrate with a growing landscape of distributed energy resources, and we've got to be low emitters of greenhouse gas emissions. So, this technology set between, smart devices, existing traditional control systems, and the smart building software gives us this mechanism to scale across all those systems, all those data models, all those equipment configurations that we encounter. And they give us also this growing footprint, right? Like, these technologies, just for efficiency alone, are being more and more increasingly adopted in the stock. So we have this base, this toehold with that software-based infrastructure that we can use to rapidly deploy the more advanced solutions that we're looking for our buildings. I would like to thank you for your attention. That's the conclusion of my prepared materials for today, and I'm very happy to answer any questions that may have come to mind through the duration of the talk.
Thank you so much. And a round of applause, virtual and real, for your talk. Thank you so much. Questions from the audience, both through virtual and in the room. Let's see, chat. Feel free to unmute and speak, or else put in a chat. Well, I'll kick it off, and I'll enjoyed it a lot. Especially the part where you talk about how you work with different companies and all of that, and I think that's the way forward and value for for progress. I wonder, you know, you mentioned the Inflation Reduction Act, the bipartisan laws and all of that, but do you see any more requirement from policy to push these out, like more stringent requirements on buildings, new buildings, existing buildings to actually use these technologies?
Thank you for that question. Absolutely. You know, I'll give one example that we're investing heavily in nationwide. We have, for the first time ever, a critical mass of state and local jurisdictions who are pursuing building performance standards. So those are effectively speaking to either energy or emissions as operated requirements for existing commercial and multifamily buildings. And we've never had that. We've had new construction and major renovation requirements, but nothing for our existing buildings. And that's critical. 75% of our, that's at both commercial and res, 2050 stock is already built and in operation today. So what those policies we look to really drive are, first, just attention to that as operated performance level. We know that there's on average 6% savings from all of our work in commissioning. We know that when we bring in the monitoring-based approaches, like with FDD, we can see 9% savings extremely cost effectively. So if you're an owner out there confronted with, you know, new performance requirements coming down the pike, this is an extremely useful pathway to meet those first compliance cycles. And so I look to that policy as being a huge driver, not just for attention to retrofits and those capital investments, but also to that really low-hanging fruit of operations that is a draw for these technologies in the first place. So thanks for that.
Yeah. There's a question in the chat. What do you think about the status of day-ahead, intraday prediction strategies for demand flexibility? How do participants actually provide an estimate of their flexibility potential in the industry?
It's certainly where we're going. The ability to do predictive optimization. So if I think about kind of like this stack of approaches, let's get things working correctly so that we can reliably flex load and do so with assurance that we will not impact occupants in unexpected ways or unintended ways. Then let's get our just kind of day-to-day best practice efficient controls working. And then let's bring in best practice kind of standard strategies, which will not tend to be predictive, right? It's more, let's employ the strategies that we have. And if we're in, say, demand bidding or other kinds of programs that requires to actually deliver a load, that's kind of a real-time adjustment, like, oh boy, I'm not making my target. I better be more aggressive in the response. And then when we're, then we think about how we're moving into the more nuanced kind of predictive strategies where the actual sequence and mechanism of response may fluctuate from day to day. And that's certainly what we're very interested in the research and with some emerging offerings in the marketplace today.
Cool, thank you. Other questions?
I think as we wait, I want to address the second part of that question, which is around estimates of flexibility potential, because there's so much more that we could do there. If you think about where we are today and where we really want to go, the really ideal case is if our buildings are going to be the kinds of assets that we want them to be in terms of providing firmed and reliable resource and asset to the grid, then we would love to be able to reach a state where we're able to quantify and communicate how much flexibility is available in a building at any given time. I could go up this much or I could go down this much. And so I really appreciate the second component of that question, which really recognizes the value of being able to do some of that.
Cool. And in the meantime, another question came in. So there we go. What do you think is the role that IoT infrastructure can play in the future to better support demand response projects and grid interactive buildings?
Our IoT infrastructure, I see like one of our, it's kind of a, you could be of the perspective that we are in our most like data rich time ever for buildings. Or you could remain kind of like, oh man, we're still extremely data poor and we don't have all the information that we need. So I think the promise of the IoT is just that cost-effective and rapid expansion of the measurements that we have available to us to inform our various applications.
Oh, wow. And then how does these outdated buildings with outdated MEP systems affect the deployment of these technologies or installation times?
Awesome question. We know that things get harder and harder and harder for control improvement and control automation. The farther back in time we go, the more and more legacy our system is. And what that, I think an open question that I'm really interested in is how do we bring about like methodical approaches to understand when existing infrastructure is like, okay, enough. And so we can improve and kind of up, like reprogram controls and just get them into better shape versus when is it like, nope, I really need to pull the trigger on investing in a whole revamp and upgrade of the system. So that update versus upgrade and where that line falls, I don't know that we have great, repeatable, formalized mechanisms to decide that. And I think that's at the heart of your question there, Thomas, and thank you for asking it, because there is a certain point at which you really are just better off first doing the control system revamping and modernizing the control system before you try to do all these things.
Yeah, totally. Another question that I have two questions, but one of the questions that was really as you were talking about it, and at the end you mentioned it, you have we have a retiring workforce, and the new workforce expects a lot. So somehow on people like me who teach a lot, like what should we teach at this point? Like where should things go, and to have the workforce that you would need for all of this? Or what should people learn? Let's put it the other way. What should people learn to be useful in this brave new world?
Yeah, and which part of the workforce are we talking about?
Any at this point, right? I think.
Yes, I think for the definitely for the operational community, I think that really there's just very interesting work to be done here around how new technology is integrated into organizational processes. Like that's not building operations specific, right? That's like anytime you have new technology in organizations, and really being able, so there's the like dimension of standard operating procedures kind of incorporation, but then there's also how are we working to evolve tools and practices and full embrace of the information that can be provided through these software tools. Like we all have plenty of anecdotes, operators who, are very into the BAS, use it more like a remote control all day long. Those who never touch it, care not to, and certainly wouldn't trust a third-party tool coming in to control. So I think those are definitely like evolving the tools of the trade, and trust and confidence with them is important. I think other things that we're seeing come up for different portions of the workforce are like how to confidently design and specify like large electrified systems where we don't have well, it's not just capacity, but like we don't have decades of experience with some of those systems and all of their varieties and configurations. And so I think that there's probably something there for us as researchers and instructors as well. Those are two examples that come top of mind, and I think they reflect different portions of the workforce and like tools used upfront versus tools and new processes that are used throughout the operational life cycle.
Yeah. So that somebody asked how they can connect with you. Is there an email or a website?
Yes, I am, J Granderson at lbl.gov.
Oh yeah.
Searchable on Google as well as my address. I could put it here in the chat as well. And
Yeah,
then,
please.
I provided one of our websites, but we certainly have more across the portfolio. Can I type and talk at the same time?
But yeah, if you Google Jessica Granderson LBNL, you come straight there. Cool. Okay, very nice. So, oh, there it is. Another question. Based on your expertise with industry partners, where do you think the R participants suffer? You mentioned trying to match promise reduction is one. What else is there that limits participation?
There's a lot, like so many. I'm glad you asked, because whenever we talk about scale, we have to be very specific about what aspects of scale any particular effort really focuses on, because there's so many. DR is, first we have to know that it's available, and it's common, but it's not necessarily available everywhere. Our industry, we know, whether it's efficiency or demand flexibility, hassle factor is huge. So I think there's a lot for us to understand and improve in terms of customer value proposition. Some portion of the market is motivated by the financial incentive and is able to respond and participate in a way that the benefit is greater than the hassle. But I think for a full market, that's not the case. If I'm really focused on avoiding trouble calls and all the other things, like the leap from there to like, now let's mess around with my loads to get an incentive check and be a good citizen to the grid, that might be quite a lift for many entities out there. And then if you think about, generally, a lot of buildings, like you could do straightforward things. You can also encounter, the kind of spoiling factor of like, yeah, I did that once and it was a nightmare and it was really hard. And, this special system configuration, loads and services being provided, it didn't work. So that's part of what we're looking to get out there in terms of like open specifications around field tested, demonstrated kinds of best practice strategies, because I think that's also been missing. I mean, like for those of us in research, if you go to the literature and you see all the literature on different ways of doing demand flexibility, the full like specification of those approaches is often not available in a way that like, a standard implementer in the field could be like, oh, I understand this. I can now go program this in a building that I serve. So those are a couple. Thank you. Thank you, Ozan, for the question.
Very nice. Well, one final question that I had is, a lot of the work you showed was commercial buildings. What do you see the potential for, residential, whether it's single family or multifamily? Is that not even on the radar, or is it too hard, or this is, this is the lower hanging fruit?
It's definitely on the radar. And, I do so much of my personal work is in commercial buildings that I often find it useful to qualify, okay, everything I'm saying is gonna come with a bias and I'm just like out of the gate orientation towards commercial in my mind frame.
That's fair.
Like demand flexibility and residential and multifamily fully on the table. I looked at the data from some recent year from the EIA, and there was, more demand response being provided nationwide from the residential sector than from the commercial. By no means is this exclusively a commercial endeavor or enterprise. The system diversity and technology diversity is broader for the commercial sector. I think it's fair and safe to say. So just, yeah, I don't personally work a lot in residential, but that is a wide field. Lots of flexible demand resource to be had from our residential and multifamily buildings.
Yeah, absolutely. Cool. So that's it. Time's up. Thank you so much for joining us and having this conversation and this very exciting work. And I will put the recording online so we can rewatch it over and over again. And if people want to get in touch, you have the email. And we'll see you next week then. Thank you, everyone. Take care.
Thank you for having me. Thanks, everyone.
Bye-bye.